Historically, dyspraxia was called the clumsy child. Is that many children have an inability to carry out or learn carry out smoothly movements that they should be able to do, to be able to coordinate their movements, to time their movements. Now, in a great many cases, the problem lies in the brainstem, and it just so happens that I have a brain here. So if I hold the brain up here, the bit we need to look at is in fact this bit here, the brain stem. So if you think of an apple, if you had an apple, this will be the stalk of the apple. So this is the brain stem. It's the bit that connects the brain to the spinal cord. Now, at the bottom of the brain stem, on each side, there's a little group of cells called the inferior Olivet nucleus. And they're very clever because what they do is they pulsate spontaneously, continuously. Now they should pulsate at between 8 to 12 hertz, the same on both sides. And what happens is when they pulsate, they send a message to the cerebellum, little brain at the back here. From the cerebellum, it goes back to the top of the brainstem, and then back children that have dyspraxia is that they also have very poor spatial awareness. Now, if we go back to the brain, and if we look at the underside of the brain, the back, this area here, the cerebellum has to talk to an area of the brain on the inside, right at the very back here. And this area is all about knowing where you are in space. So every time you move a finger, a hand, a limb, whatever, that part of the brain has to know you've made that move. Now, quite often, the cerebellum, normally on the left, doesn't function as well as it should do, which means that the area inside the brain here is under-functioning. It hasn't got the information it needs. If the brainstem isn't working as it should do, if the cerebellum isn't working as it should do, then you're going to have problems in terms of spatial awareness. You're going to walk into things, knock things over. You're not going to be aware of things around you. You're not going to be able to time your movements. In a nutshell, that's dyspraxia.
Dyspraxia is a related specific learning difficulty. This is the child that has difficulty being in space, holding a pencil, sports skills are affected, and mathematical skills can be affected too.
We know that learning disabilities in math, or dyscalculia, impacts people differently at different ages and different stages of development. We also know that there's a visual spatial component that's very important to the learning disabilities in math area, and that it's not just the numbers or the concepts underlying numbers that individuals with LD in math have, but also the language processes, the language of math that creates problems for these individuals. So when we talk about dyscalculia, we're talking about a specific learning disabilities in math. Specific. So what are some of the presenting problems that individuals will have when they have dyscalculia? Well, clearly, in young children, you will see difficulties with recognition. Children with numbers learning disabilities in math, those with dyscalculia, often have difficulties visualizing what that math mental number line looks like and how it works. Counting is something that these children also struggle with. Not just in the counting of numbers, the 1, the 2, 3, 4, and 5, but the procedures involved with counting and the principles that underlie how it is that math happens and counting happens. They often have difficulty estimating and doing mental math. So if you look at a group of pennies on the table, they may have difficulty estimating how many there are on the table without actually counting them out. And doing that mental math, doing those kinds of approximations that help you get to an answer more quickly, those are things that children with dyscalculia, learning disabilities in math, will often struggle with. Measurement is something that becomes difficult over time, not just measurement in terms of length, the size of something, but also weight, looking at the area, approximating time and measuring time, measuring temperature, and then certainly as they get older, being able to manipulate.
Stanford University may have made a breakthrough in identifying which children will overcome the handicap.
What we found was using these brain imaging methods, we were able to predict with over 90% accuracy which child would learn to compensate on a one-to-one basis.
Researchers know that the brains of some children can learn to compensate for the disability.
Records the EEG or the electrical activity of the brain in real time, allowing us to watch the brain as it performs various functions and then detect even the slightest abnormality in any of these functions: vision, attention, language, audition. A program called Brain Electrical Activity Mapping then triangulates the source of that abnormality in the brain. And another program called Statistical Probability Mapping then performs mathematical calculations to determine whether any of these abnormalities are clinically significant, allowing us to provide a much more accurate neurological diagnosis of the child's symptoms.
I used to turn my bed over and get in really big rages. I don't get so annoyed anymore.
Times tables has got a lot easier. Now I can just recite certain ones.
In educational kinesiology or brain gym, we use a lot of noticing with the person themselves. Are you thinking clearly at the moment, or are you foggy-headed? Her description was that she was tired inside after school. The body is what we call high gear, like when you're cruising in a car. Then things are easy for you to do. And any of the muscles contact instantly. If the pathways are hard work, they're using up a lot of energy, or you're thinking about it first, then you get what we call low gear responses, that the muscle doesn't immediately lock on.
Using one arm and one leg, they're opposite sides. So then they make both sides of your brain work in
Between the
together.
right and the left brain, there's this large connecting motorway called the corpus callosum. When we're first born, very few, if any, messages go across it. And the first 18 months especially, but actually up until we're 8 years old, it starts to develop and to open up and to allow information to be shared between one hand and the other. In people with dyslexia, dyspraxia, autism, and a lot of other things that aren't labelled, that doesn't get fully open.